everyone. So I will continue today on what we started last week in the form of introduction to connectionist modeling and how to utilize them for linearly separable patterns or nonlinearly separable patterns. But before I start, I would like to remind you that on Friday noon, I will post the first assignment, as I mentioned to you in the email. And it will be due 1 week after. And as I mentioned as well in a prior email, the assignments will be fully individual. So students have to do their own, develop their own software, their own results, their own analysis. So I would appreciate very much if we keep it that way, because this is an individual type of work that I would like it to be done by students on their own. So today we embark on the essence of classification system, prediction systems for more complex type of structures. So last week, let me summarize within these slides. Last week we spoke on developing the decision boundary, which separates between two classes. And these two classes, when they are linearly separable, we said that using the perceptron theorem, that there exists a decision boundary that is going to divide between the two classes. If the two classes are far away from each other, then there will be a smaller number of iterations. If the classes are close to each other, similar to what I am showing here in this particular image, then the decision boundary is going to be a little bit difficult to be obtained, especially when we are utilizing a large amount of data that are close to each other. So that is a complexity when we are dealing with the decision boundary of two classes. As you can see in the second class here, which is the nonlinearly separable, using the perceptron theorem, there doesn't exist a decision boundary that is linear. So when I speak of linear here, it means linear, it means hyperplanar type of decision boundary. When I say linear, it means that it's in 2 dimensions. When I say it's a planar, then the classes are located in 3 dimensions. And when we say that it is hyperplanar, then the dimension is more than 3. So you can see here in this particular representation here on the right-hand side that the system is nonlinearly separable. So there doesn't exist any perceptron or any other line that are able to separate between the two classes. And this has been major shortcoming that was witnessed by people who were dealing with pattern recognition. And they came to the conclusion that connectionist models or artificial neural network models are not able to separate between classes when they are nonlinearly separable. And there is a problem there because a lot of the classes have this particular type of boundary. So today we are going to extend between what we saw last time in the form of the Madeline. Remember the Madeline? We said that the Madeline is the system is able to separate. So that is able to separate between two nonlinearly separable classes, similar to the exclusive OR function that we spoke about. And I am providing here an example of the exclusive OR, which was, as you can see, the complexity even for a very simple type of gate here, logic gate, which is the exclusive OR, that the system requires 3 other lines, let's say. I mean, 1 other line here, another other line here, and another other line here, which is a gate. And as you can see the complexity, I mean, the more we have non-linearly separable type of behavior, the more complex the system is. And this, I mean, in order for Widrow to come up with this particular structure, it required, I mean, quite a bit of work. So this is not an automated type of solution, and it doesn't provide us with an advantage over other pattern recognition type of classifier. And this particular fact has led to the dwindling interest in the area of neural network in the early 70s and mid 70s, until the appearance in the late 80s of the major algorithm known as the propagation learning algorithm, which we are going to see today. So we are going to talk today about how we can expand beyond these type of structures and make them, make a neural network more useful and more adaptable to classifiers when the boundaries are not linear. So comment here, despite the successful implementation of the Adeline and the Madeline units, researchers, were not very much motivated to continue in this area because most of the structure are non-linearly separable type of systems. And this is an example here that I provided, in the last set of slides last time, and you can look at it. I would like you to go over it. I just wanted to mention one remark for this particular slide and the remainder part of the example under this set of slides, which was posted under fundamental of artificial neural network. Notice here this particular vector. So we have vectors that have input and they have an output. So the output is the class. So it's either -1 or +1. So that's class 1 or class 2. I would like you to notice the fourth element here. Okay, so the fourth element here is similar for all the vectors of the input. What is this fourth element? This fourth element is no other than the value of the input to the bias term. Remember what we mentioned in the early slides? We said that, let me go back to this particular slide here, when we include the theta within the summation. I have responded to some of you, on Piazza. Remember that what we have, so we have included this theta as starting with x0, where the x0 is equal to -1 and omega I is equal to the theta. So that theta now is included in this particular summation. So instead of having a certain type of, similar to the perceptron, where we have developed the algorithm, so let me go back to the perceptron here, where we have developed the algorithm for omega I and theta. So we don't need to do that when we are dealing with the Adeline. So that's I mentioned last time, and I would like to repeat it. So the example that you have at the end of the slides targets that particular aspect. Okay, so this is an example here where the theta is included in the vector. And I'm going to include this as well in assignment number 1. So you are going to have an example of this particular form. So the fourth element denotes the bias term, the input for the bias term, which is the theta, in order for us not to have to updating mechanism for the theta. So that's what I just wanted to mention here for this particular example. So you have the 3 input here in the 3-dimension space, in the 3-dimension plane, and here the same thing, but we have this -1, which is the 4th dimension, but it's an artificial one. So even when we are going to draw these particular vectors, they are going to be drawn in the 3-dimension space. And the last item here is no other than the input, the artificial input to the theta. So that's what I just wanted to mention. As you can see here, the first random value for the theta is equal to 0.5, and its input is equal to -1. Okay, so we don't need to do an updating using the theta when we are representing the system in this manner. So that's one question I think one of your classmates has asked me, and I wanted to clarify it to you and include it here in this example, which is the case study, which you find it at the last part of our lecture last time. So let's go now to speak on how to solve this particular problem, how to create this nonlinear boundary for the system using a more complex system, which is the artificial neural network based on multi-structure type of system. So this is the multi-layer perceptron. As I mentioned to you last time, depending on the time we have, I may or may not go over radial basis function network. So if I go over this section, then it will be part of any assignments or any type of quiz. If we don't go through it, so this is material for you to read. And I will remind that when I will provide you with the material that is included in the quiz form. So let's start with the multi-layer perceptron. So what is the multi-layer perceptron? Multi-layer perceptron is no other than a set of neurons that are connected with each other. And people have discovered, even in the early 70s, mid-70s, late 70s, that one particular perceptron, even one particular adeline, are not suitable themselves to create a nonlinear type of boundary, simply because the linear format of their output is linear by their nature. So we don't have any nonlinear activation into the system. So we have sine signum space, signum function as the activation function, or the step function that provide us whether the system belongs to one class or not. And the activation function has no nonlinearities to be expressed and to be utilized for any type of boundary function. We are going to see here that with a very powerful algorithm known as the backpropagation learning algorithm, that this is possible to generate activation functions that are nonlinear and themselves are going to generate nonlinear boundaries. However, in the early 70s, even in the early 80s, there was no algorithm possible to provide us with that particular boundary using different activation function other than the sine function or the step function. So the multi-layer architecture was proposed in the late 60s, but people were not able to develop it and to utilize it because we did not have powerful algorithm that is going to tune up the weight of the system, similar to what we are going to find here, and which was solved in 1986 by a group of researchers, including Jeffrey Hinton, who has, by the way, come up with a number of breakthroughs in the field of deep learning, which we are going to see later on. So let's look at the multi-layer perceptron here. What is a multi-layer perceptron? Multi-layer perceptron is no other than a feed-forward neural network. So that's the architecture is feed-forward neural network. It has an input network for the system, and it has an output. So the input is this set of, this is the layer, the network input. So this is where the features of the neural network are going to be imparted to the neural network. And this is the engine. So this is the engine basically, and it is composed by a set of elements that are connected with each other. Notice the connection with this particular neural network and the generic type of connections, that each one particular neurons, which is located here, has a summation feature and it has an activation feature. So this symbol means an activation feature. I'm not saying anything about this activation at this stage, but saying that it's a filter for now. And look at this output of the system goes to every element in the subsequent layer of the neural network. The same thing here, each neuron here that has been fed by all the inputs of the system here is going to generate output that are going to feed subsequent layers. So that's how it works for the multi-layer perceptron. So we call it multi-layer perceptron because we have 1, 2, n layers for the system, and all of it is composed by perceptron elements that are connected with each other. And at the outset of the neural network, we had what is neural network type of output for the system. So this is the overall structure. This is the most generic structure. This is taken from my textbook, and I'm reproducing it here for you to look at it more clearly. So this is the overall structure. I have another structure similar to it, but it's going to showcase us how to utilize the multi-layer perceptron network system. So for the backpropagation learning algorithm that has been discovered in 1986, we are going to utilize, let me show you exactly what we are going to utilize in this particular multi-layer perceptron. So this is the schematics. So this is the generic representation of a neural network. So we have the input layer, we have the output layer, we have several layers of the hidden layers. Each one is connected to the other one. So the multi-layer perceptron, what it does, so we have the actual output layer, and also we have the set of target outputs. What are these set of target outputs? They are no other than the labeled data of the signal that we are using to train the system. So these are the real values that the system should expect when we are injecting a set of input layer. So there are two types of outputs here. So there is the output of the neural network, the actual output of the neural network, and then we have a set of target outputs. So what we do, we simply create a difference and then we square it. And then what we are going to do, we take these particular errors for each one of the layer outputs, we sum up them together, and we inject them back to the system. We inject them back to the system. And this is what is known as the cumulative network error between the target outputs and the output layer. So this is one of the most important components of this particular structure of the backpropagation learning algorithm. And that's why we call it backpropagation learning algorithm. Once we are secure about this particular cumulative network error, then we are going to take it and feed it back to the system one injection at a time. So we start at this particular level, and then at this particular level, and this particular level, and this particular level. Why? Because we would like to update these particular weights in conjunction with this particular error. So we would like to minimize this error. So that's why we say that machine learning algorithm, which is the backpropagation learning algorithm, is no other than an optimization problem. And I will show it to you in the next set of slides of a cumulative set of errors. So what are these type of error? So this is the error. So the error is the number of outputs. So this is Q. This is the kth training pattern, the pattern that we have injected to the system. And this is the target value minus the actual output of the network. We squared them. Usually we put 1/2 here, but in an optimization algorithm, whether we put 1/2 or 10 or whatever number, it doesn't matter, but I will go back to that in a few moments when we are going to develop the gradient descent for this particular error. But this is the general cumulative error. Why we say it's cumulative error? Because it's we sum up all the errors for each one of the outputs. So ith represents the ith neuron of the output layer composed of Q neurons. So the output of the network has Q. It is designed to update. Look at this particular definition. We would like to update the weights in the direction of the gradient descents of the cumulative error. So what we would like to do, we have an error. We would like to minimize that error. So an error, let's say, in a certain type of shape, we would like to take that error from a certain location of the surface error to the lowest element of that particular error. So it's again an optimization algorithm. So the backpropagation learning algorithm is an optimization algorithm that is meant to minimize the error of the system. Okay? So this is the picture. Also, this is taken from my textbook, and it shows how we utilize the error backpropagation algorithm for this system. So there are two types of objective functions or error. Okay, so there is what is known as the batch learning error. What is the batch learning error? So the batch learning error is simply the addition of all the errors that are due to each one of the training patterns. So we have here n training patterns of the system, k equal to 1 to n, and we have q type of output for the system. So here we have double summation, which means that we have the target output and the actual output of the system. We have double summation here. One is related to the number of output, and the other one is related to the number of training patterns. So this is used as the batch type of learning. We are not going to utilize batch learning in this lecture. We are going to use another type of what we call online learning for the system. So what we have for the offline learning, we have two objective functions. So the main goal is to minimize subject to the weights, which are the parameters of the system. Remember, that's the elements between various type of activation functions are connected with weights. So what we would like to do, we would like to improve this error subject to these weights. These weights are called the hyperparameters of the network. So we would like to tune them up so that this error becomes minimum. So this is for the offline training, or what we call also the batch learning or the batch training of the system. It's given by this objective function. For the online training, which we are going to utilize in this course, we have, as you can see, error at once. So we have the kth training data here, and we would like to minimize the error subject to that particular training data. This is similar to what we have seen in the perceptron and in the other line. We take one training pattern at a time, and then we see whether that training pattern has been well classified or not. If it is not well classified, then we go to the next training pattern, and we see we improve the weights, we update the weights, and then we go to the next pattern. We see whether it is classified or not using the boundary that we have just formed. And if it is not, then we update the weights until that particular pattern has been adequately classified. We are doing the same thing here, but with a much more complex structure of the neural network, where we have several types of the output here. Okay, so this is the optimization problem. This is the most important equation, but the problem how to solve this particular equation, because this equation is no other than function of the weights, because this OIK is no other than a function of the weight, because it comes at the outset of the network. Let me go back a few slides here and showcase you that in order to obtain this output layer, you have to feed the network from this side, and then the network goes through this type of weights here. You see these weights, these activation functions, these activation function, these activation function, until it reaches the output layer, and then it goes to the output component here of the system. So this element is exactly similar to this element. So that's why we have each one of the output layer is a function of multi-values of the weights. So we would like to take this particular error and we would like to optimize it as a function of these weights that are changing. Let me also mention one thing here. These particular type of activation function are going to be utilized as nonlinear function. So most of the time we are going to take them as the sigmoid function. Why we take them as the sigmoid function? Remember that the activation function could be a step function, it could be a signum function, or it could be a nonlinear function. It could be the sigmoid function, which we have shown in previous type of lecture. Why we take them as nonlinear and smooth? So the sigmoid function is infinitely differentiable. Simply because the gradient descent, when we are going to minimize this error subject to the gradient descent, we are going to have values that have to be continuously differentiable, because gradient is differentiator. So if the function is not differentiable, then we cannot obtain values for the gradient. It becomes equal to infinity. So that's why the activation function here have to be infinitely differentiable type of activation function, and we utilize the sigmoid function here, as I mentioned in this slide. So we use the sigmoid function as the activation function for all the neurons. So this is, in this particular slide. So let me stop here before we continue and check if any one of you has any question before I continue. So I have shown you the architecture of the neural network, how we are expanding beyond the structure of an Adeline here by having multi-layer, and now articulating the machine learning algorithm for artificial neural network as an optimization algorithm that is meant to minimize this particular error. So I'll stop here for now, and I would like to hear from you some questions. Can I hear some questions, please, here, if you have any? So I will stop from time because I received some feedback from your friends. To respond to you. So I see here. Can you explain the double summation and the summation for the offline online? So let me do it again. Okay. So we have here. This is let me look. So this is one single summation. So what is this summation here? So this summation is no other than the summation. So it's the summation between each, the square, the error between each one of these outputs. So each one of those is one value of the Q. So we have a Q output here. We have Q set of targets. So we simply do this one minus this one. So this is the target value, what the system is expecting to have. This value is real. And this is what the system is giving us. So we take one at a time. So we take this one and minus this one, plus this one minus this one, and we square them. So this is what is this particular. So Ti minus K minus OIK. So this particular summation is a simple summation of all the elements at the output. Okay, so this is a simple summation, which we find it here. Which we find it in this, what we call online training. Look, we have Ti minus OI. However, for the offline training, when we are dealing with many training patterns, so what we do, we generate the first pattern, and then we generate the second pattern, and we generate the third pattern, and then we have the cumulative values for each one of them. So for the first one, we have this summation. For the second one, we have this summation, and then we generate the first. So for each element of the training points, we have this particular summation for this element, and then we concatenate all the errors. Each one of them has been obtained for each one of the training data. So this is what is known as batch training. So you launch all the data at once, and then you compute the error. So that's what is batch learning, which we are not going to see in this course. This is what we are going to do. So we are going to generate one training pattern at a time. So the first one, and then we try to minimize the error and go back and update the system. And then we generate the second pattern. We do the same thing and we go back and then generate the third pattern. So that's what we mean by the double summation and the single summation. So the second question, is there any difference in the MLP performance if you use batch versus online? Very good question. So people use both, okay? So the batch training sometimes is efficient when you have enough memory within the system. Sometimes it's not efficient. Sometimes you find better results with the online training. But if you have big memory, putting all the data at once might generate for you at the end easier or faster response of the system. So depending on the computational resources of the system, okay, and depending on the amount of data that you have. So I cannot judge 100% which one is better, but people have utilized both. So if your computer is so powerful, with the memory is so powerful that it can handle all these type of data for large network structure, you can utilize the offline training. The online training could be utilized once at a time, but it's going to take several type of iterations. So depending on the power of your computational resources and the amount of data for your particular system. Another question, is there any, okay, in online learning, how do you ensure the weight adjustment for one pattern doesn't compromise the classification performance? Very good question, very good question. So basically for each one of the patterns, similar to the perceptron, remember what we have for the perceptron? So if one pattern has been classified well, then we are going to build the next value of the update weight is going to have already in it the weights that have already been, reserved, that have been utilized for the system, have taken into account the earlier pattern. So the system, when it does the training, it has already memorized where the earlier patterns is located. Similar things happen here most of the time, because this is a nonlinear type of training. So it's a little bit more difficult. Sometimes we might lose certain type of training patterns that have been classified well by the system. But usually the weights that have been updated as we go take into consideration the earlier type of patterns that have been learned by the system. So the boundary is going to be memorized in certain aspect when we are doing the training of the system. Okay, so let me continue now. So this is the type of question. So thank you for your question. Let me continue with this now. And let's go now to tackle this particular problem here for the objective function. So remember, our machine learning algorithm here is no other than minimization of this particular function subject to this weight. So this weight here is not scalar. So this weight is huge matrix. Actually, it is composed of all these type of connections between the various elements of the system. So what we would like to do here, so we are going to utilize the gradient descent for this particular system. So let me explain what is this gradient descent. Okay, so let me, 1 second. Yeah, so let me utilize here, comment here, and let me explain for you, draw. Okay, so let's suppose that we are dealing in a two-dimensional system, okay? So let's suppose that this is the error, this is weight 1, and this is weight 2 of the system. And we are going to presume we have the most beautiful type of error, quadratic type of error, similar to the paraboloid type of error for the system. So let's suppose that this is the quadratic error. So this, let's suppose that this is E, okay? This is omega 1. So let's suppose that we have only 2 weights, although in the multi-layer perceptron, we have sometimes hundreds of them, thousands of them. So we are not even able to construct the error. So what do we mean by the gradient descent? So as you can see here, the gradient for this particular curve is the tangent to this curve. So this is the direction of the derivative in the 2-dimension. Okay, of course, this derivative has, I mean, if you do the projection on this particular system, you are going to have 2 direction for omega 1 and omega 2. So if this is, I mean, this is particular error here, and then we are going to have for this particular element here, its projection. So we have this particular projection is going to be over omega 1 and omega 2, and we are going to do the derivative with respect to the 2 of them. So what does that mean here, this particular updating rule? So this, it means that, so this, as you can see, this is the gradient, but we would like to update the weights so that we would like to reach this particular area. So this is the minimum of the error. This is the smallest error. Why we would like to reach the smallest error? Simply because we would like this element and this element to become almost equal. That's our main goal. But this is a very complex structure because we have omega 1, omega 2, omega n, but I would like to showcase it. So here you can see that the gradient is in this direction. So what we mean by here, so this sign means that we would like to go against this particular vector. So we are going to go this particular direction while multiplying it by a small element here, which is a parameter eta. And this smaller parameter, the more closely you are with respect to this type of error surface. So the error surface is in 3-dimension. So we would like to go this way until we reach this particular area. So we would like to go further and further and further until we reach very small value of the error, where dE with respect to dOL, omega L, equal to 0. Once the derivative is almost equal to 0, we are in this bottom area. And when this is happening, then the error is going to be extremely small. Note that sometimes we never reach this area here, but we get close to it. Okay, so I would like you to now to remember 2 things. First of all, the objective function, which is this minimizing omega k, this 1/2 is due to the fact that when we are going to the derivative with the square, we would like the square to be disappearing. So we create the 1/2 to have non-integer in the front of the equation, as we are going to see it later on. This minus means that it's the gradient descent. So we descend according to the opposite of the growth of the error E. So that's why this sign. Always remember this sign, because sometimes when we don't do it in the algorithm, it doesn't give us, any type of structure for the neural network. And then this is basically the gradient. And remember that the gradient is a vector with respect to all the elements. So this is composed of partial derivative for each one of the omega. So omega, it could be 100, it could be 200, it could be 1,000, it could be a million elements in neural network. So this is a succession of elements with respect to this particular error. So this is the two type of equation that I would like you to remember here. And this is one of the well-known machine learning algorithm, and machine learning using connectionist model is based on this particular aspect and representation. But this is good mathematically. But how to solve this particular problem? This particular problem is extremely complex. Why? Because remember, this value of the OIK is a function of several hundred or several tens of elements of the omega I. How are we going to go from one layer to the next, to the next, to the next? So the idea is to utilize what is known as the backpropagation learning algorithm, going one iteration at a time. So let me go back to this area here. So what we mean here, we would like to go back. So once we created this particular error, we go back here and then we start fitting the system according to this particular minimization. So we improve on the weights here. Once these weights have been updated, we go to the next weights and we update them as we see here. And then we continue until we reach the early layer of the neural network. So every time we update a set of weights, once it is updated, then we go to the next set of weights and we utilize the earlier elements that we have grasped here, and then we update the weights according to what we have gained in the form of knowledge. And this is known as backpropagation learning, because we have the forward, injecting the forward information, but then we go backwards to update the layers of the system until we reach this particular layer. Once we reach this particular layer, what we do, then we inject another training pattern. And now we are going to utilize the updated weight, the one that we have updated according to the backpropagation learning algorithm. So that's how the backpropagation learning algorithm works. And that's why we call it the backpropagation learning algorithm. And this has taken almost 16 years for people to develop it and to make use of it. So now let me go over the mathematical aspect of it. So this is the mathematics of it. And now let's presume that we have L layers. So we have L layers of the neural network. We have eta, which is this particular element, which we take it between 0 and 1, which we call it the learning rate parameter. We are going to discuss about this one. And then we have delta omega ij L, so superscript L. So what is this omega ij? So omega ij is no other than the linkage between one neuron and another one. So I'm going to show it to you in the next page. So we have several omega ij for each one particular layer. So we are going to update one layer at a time. So we are going from what I just mentioned to you, we are going to use the most advanced layer that are close to the output and then go back one at a time. So what is this connotation mean here? I would like you to remember it. It means the weight updates for the connection linking the node J, which is located at a layer L-1, to node I that is located at the subsequent layer L. So I would like you to remember this nomenclature for this particular representation. Okay, so let's now look. So this is, let me go back here to explain to you what is this, what I just mentioned to you. So this is the omega ij layer. Okay, so it connects the jth layer at L-1 to the layer that is coming after it, which is layer L. Okay, so that's the definition that we are going to use, and the nomenclature, because the derivation is quite complex and we have to agree on exactly what we have here. And the OIL is the ith output of layer L. So this is the ith node of layer L. So each layer has a number of neurons or perceptron. Okay, and all the items that are coming to excite this particular layer are going to equal to tot I. Okay, so the tot I are no other than the summation of all the elements that are coming to this particular layer. Okay, and the output layer is no other than the applied filter to this particular summation. Okay, so this is for connection. This is omega IGL. This is tot I. It's related to this one. As you can see, it's I here. It's OI. And tot I before we go to the activation function. And remember that F we choose for all these type of neurons is the sigmoid function, which is infinitely differentiable type of function. And it has this particular behavior. So if I take it this way, the sigmoid function is a function that behaves into this way. So it will never surpass the value of 1. The maximum of the sigmoid function is equal to 1, and the minimum value of the sigmoid function is equal to 0. Okay, so that's what I wanted to share with you here. So OJL-1 is the output for the neuron J at layer L-1, the one located just before layer R. Tot IL, the one I just showed you, is the sum of all signals reaching node I at hidden layer L coming from the layer L-1. This is exactly what I explained to you a few moments ago. Okay, so now what we are going to do, we are going to utilize the formula that I just mentioned a few slides ago. So we are going to utilize now this formula for every element in the set of layers for this particular system. Okay, so here I might explain it, but I would like you to look at it in more detail. So I am going to use the chain differentiation. I'm not going to go over the extreme details. I am posting, and it is posted already, a whole set of slides on how to utilize the chain rule for a system that I have developed for you. So with this set of slides, there is another set of slides that I have posted, which you can look at it in more details, and it explains to you how we did this derivation. But here, for the sake of conciseness, I have put it into few slides. So sometimes, I mean, it takes several slides to explain the back propagation learning algorithm, but I will give you the main outcome here, and then you can look at it at your own pace, because we need to, to go further in this particular component of the course. So again, now we would like to extract these particular values. So remember the delta omega i's that we have utilized in the perceptron. So now we are utilizing the ij, which connects between two type of neurons. So delta omega igl, utilizing the gradient descent formula that I just mentioned to you. So we have dE, remember that we have dE with respect to delta omega. But E is not direct function of omega. So E is a function of OI, okay? And the OI, if we go back here, you can look at this OI. This OI is function, which is the filter of all these type of element tot I. But tot I are generated by this omega ij coming from this layer L-1, okay? And the same thing here, this tot I L-1 is generated from the layer that comes before it. So we have to do chain differentiation in order for us to utilize this particular type of information. So dE with respect to d omega, so is equal to dE with respect to do and doi, but oi is also function of tot I, and this is multiplied by doi with respect to d tot. It's a little bit difficult here to write here. And then we have d tot, which is now function, finally, function of the d omega ij. Okay, so this is the chain differentiation, which is here, located here. Remember now, we know why there is minus sign. We know why there is this learning factor here, which is between 0 and 1. And I will explain to you later on what is the impact, whether it is very small, whether it is very large. Okay, so this is one of the most powerful type of equations to provide you with an update version of the omega ij. Remember that this is happening after one single training data that you have generated to the system. And the training data, of course, it has a vector input and a vector output for the system. So for the case where the layer R is the output layer, so as I mentioned here, we start with the outermost layer. So we start with this layer, which we denote layer L. Remember the back propagation, so we start from L, and then we go to L minus 1, and then L minus 2, until we reach the first layer. So that's why here, so we'll go back to the equation. We start with the outermost layer. So the outermost layer, all the data is provided to us. So we know Ti, that's the target output. We know the actual output of the system at the layer big L, that's the output of the system. We know the derivative of the system because we know the filter. So the F is again the sigmoid function, that's the activation function. Okay, so the derivative of tot with respect to L, which we also know as being the error signal of the ith node of the output layer. Okay, so we come up to this particular equation where all the data here is known. So we know Ti, we know Oi, we know F tot I, we know big L. So all of this is known. And the delta IL here for the sigmoid function is no other than this particular type of definition. The sigmoid function, let me remind you, the sigmoid function is given by F equal to 1 divided by 1 plus exponent of minus x. This is the sigmoid function. We defined it last time when we saw it in the lecture. This function, although it looks a little bit weird here, but this function has maximum value of 1 when x is equal to infinity, and when x is equal to infinity, minus infinity. So when it goes to, this becomes equal to 0. So this becomes 1 when x is equal to infinity. When x is equal to minus infinity, it becomes 1 divided by infinity is equal to 0. So that's why its behavior goes like this. That's the filter. So we don't want an activation function within neural network to surpass a value of 1, because it might be explosive if the value is bigger than 1, then multiplying by, several times, several thousand of times, sometimes will give you very large values. So we utilize this function. This function happened to have a derivative, f derivative, which is equal to, this derivative is equal to f times 1 minus f. That's one of the characteristics of the sigmoid function. So we have here the f prime. This is generic. This is general. When the function is of the sigmoid behavior, then we are going to have, this is, so this, remember, this is the function itself, that's the output, and this is 1 minus the function itself, which is here. Okay, and then Ti minus OIL is this particular part. So this particular part here is what we call here the delta, which is located here. Okay, so now this is a big finding here. We are now able to find, let me go back slide here. We are able to find now the update for delta omega L. This is a major finding. So this is with the back propagation, because we have access to all these particular values. We have this value, we have this value here. So we know what the system is providing us. So let's continue further now. Okay, and then try to see if there is an iterative type of behavior for this particular system. So delta IL is equal to this for the value that is the outermost layer for the system. Now we continue with it. If the layer is smaller than big L, then the delta omega ij is going now becoming equal to eta delta IL OJL minus 1. So remember here, this is for the big L. Now we are going to have similar type of formula, but now the delta IL is going to be different from the earlier one here, because now we are going to utilize, the chain differentiation, and the system is going to provide us with particular type of, iterative type of formula. So we are able to find that the delta IL is a function of all derivative of tet at IL times P equal to 1 to NL plus 1 delta PL plus 1 omega PL plus 1. So this particular type of form that we have obtained here is due to the fact that we are going to utilize the various type of delta L at the layers that are just before it. So for the layer L that is different than big L, now we are not going to deal with the output of the neural network, but we are going to deal with an intermediate type of output. And that intermediate type of output is going to depend itself on the delta L of that intermediate one that are close to the output layer. Okay, so we are going to utilize this particular factor. So let's suppose that we are at a layer of L minus 1, which is a layer below L. So you can see that that layer L minus 1, it gives us the value of the delta L. Okay, so the delta L, but the delta L is no other than the delta L that we have defined here. Okay, so we are coming up here to this particular iterative type of formula, which is going to utilize, the subsequent type of layers for the system. So we go from here for L. So L minus 1 here, and then we go back and back, and then we are going, so at every instant of time here, we are going to utilize the benefits of the layer that came after it. The same thing, so we go backwards one time, and then we are going to utilize every time the values that have been developed earlier. But the values that have been developed earlier, we know that they have been updated, so we are going to make use of them. Okay, so the one that comes afterwards are going to be updated, and we are going to utilize these particular values that come after the update. So this is one of the most important formula. And again, when we are going to utilize the sigmoid function, so the sigmoid function gives us the f times, again, 1 minus f. Okay, and using this way here, this particular iterative formula, so we come up now to this particular powerful algorithm for the system. So this is the algorithm for the back propagation learning algorithm. And again, as I mentioned to you a little bit earlier, there is more details on how to extract these function in a more detailed steps. So I burned the steps here, but there is a set of slides related to the backpropagation learning algorithm. I invite you to look at them in order for you to understand what is how we extracted all these particular value. So let me proceed forward now. So now we have this formula, which is helping us out extracting all the values of the weights. So we are going now to utilize the EK, okay, for the system, and then we are going to utilize this particular algorithm for the online version. Remember that we are going to utilize the online. For the offline training here, which we are not tackling in this lecture, the E is going to be replaced by EC. What is EC? EC includes all training data at once. That's the double summation. Okay, so that's the double summation. Remember, offline is for the double summation and online is for one single summation, one element at a time. So this is now the algorithm, and I would like you to remember it very well for the backpropagation learning algorithm. So we initialize first the weights and the threshold to small random values. We choose one single input and one single output. So this is a vector, this is a vector, unless the classifier is binary. But usually we might have several types of classification values for the system, several categories for the system. So we propagate the kth signal forward. So what does that mean? We inject the inputs of this training pattern to the system. And then we compute at every level, we are going to compute the output of each one of the neurons. Remember that at a particular level L, it is function of the OP that are coming from the layer -1, according to that notation that we have utilized. So I would like you to remember how to do this. OIK is equal to FP equal to 0 to NL-1 at the layer L-1, omega IP, which connects between L-1 to L, OP L-1 that are coming from all the output at layer L-1. Compute the total error, E, which is equal to EK plus E. Okay, so this is, at first it's for the first element, so we have an EK, so that's the first EK for the system. And the error signal is simply computed by this formula, where we know the TI, the target value, when we know the OIL. So remember, the I means the index of the particular output. So remember that we have several outputs at the system. So this is the ith output. That's what we mean by at output. So for each output, we have a delta. Okay. So at the layer, the outermost layer, we have Ti minus OIL. Okay. Times F prime dot IL. So this is a scalar. Remember, because the Ti is a scalar, OI is a scalar, although the whole network has a vector of output going from T1, T2 to Tn, and then multiplied by F prime dot IL. Okay, and then we continue. Step 5. So now we are going to the delta omega IL. We start with the first one, L, because once we know the L, then we can know all the other IL. So the delta IL is equal to, given by this particular formula here, okay, and that all the other delta ILs are given by this particular formula for L strictly less than L. So now we have all the values of omega ij going from the outermost layer to the first layer. And this is being done using an iterative type of formula. Look at this delta IL. Look at this. For value that is different than the big L, it's given by this particular formula. OIL, NL plus 1, delta L plus 1. So look, so it utilizes the deltas of the layer that comes after it. Okay, so this is the most important formula in the area of artificial neural network that provides you with the hyperparameters computation for back propagation learning algorithm with multi-layer system. And then what we do, once we have updated all the weights, we repeat the process starting from step 2. Step 2, it tells us choose another. This is step 2. We choose another training values, xk, tk. But now, instead of using the original random values of omega, we are going to utilize now the values of omega that the system has tuned them. So the system has started tuning that error, has started minimizing that error according to the injection of this particular type of data. Okay, so here we can say that now we started going, back, going to, not back, but going to reach this particular minimum of the system. But this is very simplistic structure using the gradient descent of the system. That's why we call it a gradient descent. So by utilizing minus eta gradient of the error, so we would like to reach this particular error. That's our ultimate goal. Once we reach it, then our values for the system has been type of updated. Okay, so we repeat the process starting from step 2 using another exemplar, which is training set of data. Once all exemplars have been utilized, we then reach what is known as one epoch training. So let me tell you what it means by one epoch. One epoch, it means once all the training data have been exhausted. So we have, let's say, 20 training data, 100 training data. So every time we inject training data, and every time we see that the system has been updated more and more. And every time we do that. And then we check if the error has reached, a very small value for the system in the output layer, then we stop the training of the system and we say that the system has been trained. We will come back to this later on when we are going to speak about overtraining of neural network and undertraining and good classifier, bad classifier. So we'll go back to that. But for now, I wanted you to understand the back propagation learning algorithm and what it means for this particular neural network. And it took scientists almost 16 years to come up with this particular type of neural network. So if the cumulative error of the system is below a certain threshold, so if what we found E is less than E desired, so the E desired could be provided by experience, or it could be provided by a customer, or it could be provided by observation, then we stop the training. If E is still large, then we go back and then we redo another epoch of training from this. We restart the system from scratch. So now, but instead of initializing the weights and thresholds to small random, we are going to utilize the latest values of the epoch training of the system. So step 1 becomes already an updated set of weight and thresholds, and then we start from step 1 and go, through all the training data of the system. Okay, so this is the various steps for the back propagation learning algorithm. I would like you to look at them very attentively. I would like you to go over the set of slides that I have posted also about back propagation learning algorithm, and I will give you more examples as we proceed forward with this particular system. So let me speak here very briefly about the momentum, but before speaking, I would like to give you a chance to tell me if you have any questions so far. Okay, so you can raise your hand, you can speak. That's fine. But please, if you have any text, I don't see any text here. But I would like you to digest this. I would like you to go through it one more time. I would like you to look at the material that I have appended to this set of lectures. So this is another set of lecture called Back Propagation Learning Algorithm in the same section of this particular lecture. Okay, but it's not in this set of slides. It's another different set of slides. And of course, the same material is posted on my chapter textbook for the backpropagation learning algorithm and for the multi-layer perceptron system. So let's look at the momentum. So what is the momentum? So the momentum is an important concept when we are training a backpropagation learning algorithm. So the momentum, it tells us how the error in particular system is being decayed. Okay. So remember, this is again a quadratic type of learning mechanism for the error. So the error could be, I mean, in this particular thing here. Okay, and this is the error. So usually, I mean, the error is in the center there. Okay, so we would like to see how fast we are going to go to decay to reach the error. Two things. If we have very big speeds of going downwards, the system might not converge. If we have very small speeds, so if we go very, very slowly, the system is going to be very, very slow, and it converges converges very slowly after a large amount of time. So this happens with values of eta, which is equal to 0.01 or 0.05. So very, very small value of the eta is not very helpful. Very large values of the eta 0.9 also might not be good, and I will explain to you why. The gradient descent requires by nature infinitesimal differentiation steps. So in order to go through this particular value, we would like to go slowly. But then if we go slowly, the system is going to go forever to reach this particular value. But that's formally, that's what it should be. So what people have done, they created what is known as momentum. So when you do, I mean, for a small value of the system here, when we go through a certain type of descent, the system is going to remember where it was in the earlier iteration. So the system has like a memory. So this momentum, it tells the system that you are on the right path of descent. Okay, so this particular system provides us with the capability of generating what is known as the modified weight update. So this is the original weight update that we have seen earlier. So minus eta DEC divided by T. But then we are going to add to it an element here. Why this element? This element, so if we are going to have it here, if we put it from the other side, this element is going to provide us with delta omega, which becomes equal, presuming that the L is very approximate to the L at T plus 1 and T are very, very approximate. It gives us a value of, instead of minus eta, it gives us a value minus eta divided by 1 plus minus gamma. Okay, so even if this element is very small, the fact that we have this particular element here is going to push the gradient descent at a faster speed. Okay, so here we have the gradient descent dE with respect to the omega add. Okay, so remember, this is a vector. This is a vector, okay, because we are dealing with L elements. So this particular element here is going to be, despite the fact that we are going to utilize eta that is small, this element is becoming large. Okay, so this element is going to be large. So again, for large learning rate with momentum, so I will leave it there. So for small learning rate with slow convergence, so remember, again, we are presuming that we have the paraboloid here, okay? So if we go with the smaller value of the eta, this is going to take a lot of time to reach this minimum. So this is the minimum here, which corresponds to this area, okay? So with the small value of eta, we would like to have small value of eta, but it is going to be very, very slow converging. However, when we are going to choose large value of the eta, then the system will provide you, I mean, the system will start bouncing between this particular set of surfaces. And even when it reaches this surface, it keeps bouncing back and forth, and it will never reach the error of the system. So this is a very bad behavior when the system is trying to take large value of the learning rate. However, with the momentum here, you can see that the system is converging fast, even with smaller value of eta. So it's going to converge to the absolute or to the local optima of the system, even with smaller value of eta. So we gain from both words. We make sure that we are getting descent to the error, but at the same time, we do it in a fast manner. And this is basically what is known as the momentum, and it has been used as a major type of feature for training a backpropagation learning algorithm. Okay, so this is basically an example to illustrate the backpropagation learning algorithm. So we have the system values. So we have 3 training type of patterns. So forget about testing data now and validation data. So we are going to presume that we are creating the system, and we have bias -1 that is structured within each one of the activation function. This is the activation function of the model, which is a sigmoid. So it's equal to minus lambda times tot. Tot is basically no other than the summation of all the elements that go to particular perceptron. Okay, so that's what it means, tot. So that's the total signal that comes from all these particular elements when multiplied by their respective weights. And as I mentioned to you, so it's equal to f times n1 minus f dot. And in a lot of the cases, we utilize lambda is equal to 1 for a sigmoid function with parameter equal to 1. Okay, so this is the structure, and this is how I would like you to build a particular neural network. So we have O0 here, we have O1, we have O2. As you can see, we are creating an artificial layer here known as the layer of the bias. So these type of bias, as you can see, so they go and be injected to every layer. So this is the first layer of the network, and this is the second layer of the network, which happens to be the output. So for each one of the layers, we inject the bias term. So as you can see, the bias term provide us with the way of having to classify 2 type of data sets that doesn't need to be, so this is particular data sets, this is particular data sets. So even if the if the boundary doesn't need to pass through this, the 0, so we create this boundary and it doesn't have to pass through this origin. So that's why these type of values are very, very important. So they are the bias term. So this is the structure that I would like you to use, and this is the connection. So it's omega-3 0 using the connotation that we have utilized in the system. We initialize the system, we apply the input pattern, we create the outputs for each one of the system for forwards, we compute the error. We found that the error is still very large. Then we go through, the delta 6 of the output layer. This is the delta L here, remember? Because we would like to try to compute the various values. So we compute the layer at the outset. So let me go back to the picture. So this is what we are trying to do. So we start improving this layer. That's omega-6 3, omega-6 4, omega-6 5. So this is how we do it. So each one of them, as you can see, is function of delta. And then now once we have this particular structure, now we create the delta 3, which is function of the delta that are in the front, the delta that are of the subsequent layer. So this is the iterative type of formula. And then the delta 3 is being provided there. That will allow us now to create the second layer updates for our system. Okay, so this is the error backpropagation for the model. And then we continue for step 2. We apply the second input pattern, but at this particular stage, we utilize the value of the omega-3, omega-3 1, omega-3 2, 4 2, 6 5, all the values of the earlier iteration. So these are the new values that have been updated. They are no longer random. And then we continue with the system, and then we compute the delta 6 here, as you can see. Okay, and then we continue the system for the second training pattern. So these are the improved value for the new weights, and then we go to the delta 3 and we utilize the new values for the delta I and the omega updated for the system. Okay, and we continue forwards with training of loop 2. Now we go to loop 3. We apply, so this is actually, it's called the third pattern. So this is a mistake. We apply the third pattern because that's the third pattern. So I will fix this typo here. And then we proceed forwards. We compute the error, and then we compute the value of the system. And then we found out that the error after we did all of this is equal 0.1237, which is higher than 0.01. So which means that we need to keep updating the system and keep improving it by the next epoch, by doing next epoch. Okay, so sometimes we require hundreds of epochs within the same training data in order for system to converge to a particular set of values. Okay, so that's what I wanted to showcase you here today. So that's the backpropagation learning algorithm. It's one of the most important lectures in this course, but I would like you to get help from the additional material that I have posted. I would like you to look back at how we derived these particular equations. It's straightforward if you look at it mathematically, but you have to go into the intricacy and see how it works. You can look at many textbooks or many material that has been published about backpropagation learning algorithm, and you can look at it and get help with it. If you have any question about it or anything that you did not understand from this lecture, let me know. But now I will take, the last minutes to answer any type of question that you might have so far. So you can look at the example again. I went step by step and with the 3 type of training data. So so if you have any question, I will be happy to listen to them before we end this lecture. Feel free to text me, so I'm reading the text. If you have any text, I will be happy to read it. If not, then please feel free to let me know or email me or my TAs, and I will be happy to respond to you. I strongly suggest that you join Piazza. There are a number of questions that your classmate ask, and I try to respond to them within a few hours of time. And if you don't have any questions, I will see you on Friday on Friday for the completion of backpropagation learning algorithm and material related to it. I will give you another example, and then I will start discussing the training versus testing and what we mean by overtraining, what we mean by undertraining, to illustrate these particular various aspects. Okay, so if you don't have any questions, thank you very much for attending, and I'll see you on Friday. Have a good day.